Hello everyone. Uh, this is the second part of the concrete compressive test. In the previous, we used a standard solver to get the response curve, and now we want to change the solver from explicit to from the standard to explicit. And the other thing is that we want to consider some failure behavior in the column. And the third part is we use the previous loading capacity curve to apply load instead of displacement. So here is the capacity curve of the previous example, which is this one. And now we found out this is the ultimate force and corresponding displacement is about 5 millimeter. So we use this load instead of displacement, and we want to measure the response of the structure again. Okay, I go to back here and the modeling is completed. You can check the previous tutorial and see how you can model, and then come back to here to see how we will apply the explicit. I want to make a copy of this one, model 2, and in the model 2 we will just focus on the model 2. And the first thing is I want to change the step, which is deleted the static step and delete it, and I want to create a new step called dynamic. So we use explicit dynamic solver, but the loading procedure is equal to the previous one, so which is quite slowly. And now I'm going to back to here dynamic and taking explicit. In the explicit, instead of 10, I give 5 seconds to here. This is 5. Even I can give 2.5 seconds. So the entire was 10. So this is about 5. So I can give 2.5 seconds. So 2.5. So the loading procedure is static, which is slowly we apply the load. And the other part is we can assume default. Now, in the time history output or field output, I want to select some parameters. So the first is I want to get the failure, so damage and tensile damage, compressive damage, and also some failure from the plasticity behavior, and it's okay. And output. Now we want to create some set. In the previous one was displacement here, and now the acceleration is here. We want to measure the displacement here and the acceleration in the reaction force or F2. We have go to the set and we have loading point, and I'm going to call reaction or REF. Selecting this point. In the previous, the same was from the one. Now we have to create different set, and this is called loading, which is we want to, so each interval of like instead of interval I want to use go to displacement u2 every unit of time, so 0.1 second. And the second one is REF, and the same step, going to set and REF again, not displacement, but this time is going to be take the reaction force and using the same interval to measure the displacement and reaction force. So we created two. Even I can go to rename it u2. Now we have two time history output. So the next thing is we go to the interaction is also completed, and load is also going to the load. Now we create the concentrated load using in a dynamic and selecting that loading point. So the amount of load is minus giving this load. Copy and this one. So sometimes it requires amplitude. Let's define an amplitude. So we have 0, 0, 0, 0, and we have in Z, 0.5, 1, 1.5, 2, 2.5. So here going to 0.2, 0.4, 0.5, 6, 0.8, and this is 1. So in the until time is reached 2.5 seconds, so the 100% of that load will applied slowly. Now okay, amplitude, and next we go to define a boundary condition is already given here, and so load is finished. We go to mesh. In the previous one we used standard. Now we have to define the explicit. Here is the explicit. It's called OK, and then go to the column, and here again I should select explicit. And one more thing, we want to see the element deletion. Here is element deletion. We want to activate yes. Mostly the concrete will delete it because we want to define some shear failure for the concrete, not for the steel rebar. So that's for the rebar is no need. And straps, again I want to apply explicit. Now we finished and everything is completed. So the last thing is I should define the go to the model 2 and edit keyword. Now we want to define some concrete failure. So the concrete failure does not exist in the user interface, but we should define in the edit keywords. So now I go to here the concrete. We use concrete tension, compressive damage and tension damage. I come here. This is here, go to exactly the down and then just here and write star and called concrete failure. Now here ask as what kind of failure should be based and what kind of failure, so I should give type equal, I want to use strain. So then giving a down, and I want to give the first is this one, the last step of concrete compressive damage, and just give comma and space, and the second one is this one, the last data from the tension stiffening or tension damage. Copy and paste it, and then comma again. So now we're bringing the corresponding the damage parameters for this one, and again space and bringing this one. Now we have got 4 parameters. Now I say OK and we go to the job. In the job we want to create, this is the second mode, model 2, called model 2, and submit it. So this is the error. It asks me, here is one illegal value because the spelling is wrong, so I should fix this one. Go back to here, edit keywords, and I should write that one strain, and that was that. You see here one R should be considered strain. Submit again. Now we can monitor and see. So it's starting, and first step is 0. This, and it will take some time because we use a large time period. After finish, we will see and discuss. Now the analysis completed, and we want to see some results, both model 1, model 2, the result, and here is the result, and nothing is left because we activate the element deletion, and also we considering failure, so the entire structure is failed. Let's see when it start. The step output is very 0.1 second, so in case if I let's go to, this is the output. And just this part is left, otherwise deleted during the failure. Now I'm going to that's the previous one. I'm going to delete this one and create a new output, and here is, and now we have two curves. One curve is one curve is, and this is already 2, and this is the displacement. The displacement here is very slow, very less, and then suddenly it dropped. Let's see how it works. So going to here and operate combine, and for the u2 we should -1 times -1 and times u2. Otherwise just REF2 is okay. Now I can call it FET2, and I go to plot both, and we can see it's a little strange. Let me show you the plot one, and here is the procedure is like we applied the load, and then it reached to the ultimate and then dropped suddenly. You can see the displacement is very large in this point. If I go back to here um, edit, and here in and this is y is the force and this is the displacement. Yeah, edit, x is displacement, so in this point it reached 0, so we don't want this part, and just this part is our copy, and we go to back here to the Excel and paste, and we can create select, and if this called FED1, and we want to get one FED2, so this is FED2, and here is the y. Now you can see this is the graph. When we apply it load to maximum this point, the structure totally collapsed, and the entire elements, because of the shear damage, because of the concrete damage, it destroyed. Now like this. I'll go to option and list okay. In the last step, just one step left, it will and this is the 2.7, and the last step it will destroy all the structure, because immediately most of the element reach that point. We should do one more thing to get slowly, so we go to that step and change this output to be every 200. Let's take a little larger, and this one both should be used every interval of 200, and this also 200. If I rerun, it takes some time, so you can do it by yourself, and I give this model to you. And this was the second part of the reinforcement concrete behavior under the compressive test. And the third part is we want to retrofit this structure. So now we have the capacity is 2800 kilonewton. We want to improve and using CFRP how these behave. So that's the next tutorial, and keep tuned, and we will see you next time. If you have any question, please put in a comment and we'll find time to answer you. See you next time. Hello everyone. This is another tutorial which we will retrofit an existing beam which previously we model and simulate, and we got the curve of force displacement curve, and I'm going to plot it, and here is create another operation and using combine, giving -1 times the u2 and comma -1 times and now I can call it FED, force displacement curve, and now plot, and this is the curve. Now what we're gonna do is we want to retrofit this existing beam using CFRP material. This is a CFRP material, and the thickness of the CFRP is 0.146 millimeters. So we will consider each layer, a composite of each layer. So then you can say the total equal this one times 0.146. So it's 1.4 millimeter. This is a very tensile with a very high tensile strength material. We want to retrofit, and then after the analysis completed, and we want to compare the results with the uh, existing beam. How this CFRP can improve or enhance the beam load bearing capacities. So we go back to the part. Uh, because we already created beam concrete beam, rebar, and straps and support. So I suggest you to watch this in the 3-point bending loading tutorial, and then come back and just create one more called CFRP, carbon fiber reinforcement polymer, and then select the shell, and you can give at least we want 5000 and use extrusion. Now here the size of the this CFRP is equal to the size of the concrete. The size of the concrete was 200 width and 300 depth. So and I could give minus 100 and comma minus 150. So this is the first point. The second point is 100 and 150. So we created the section and we want to extend it to 2 meter, 2000 millimeter. Now we created the CFRP or another box. We go to properties. In the property, we should create a material for fiber elements. So for concrete, we have CDP, which has a 25 kilo megapascal, and steel rebar, which has ultimate strength of 410. Now in my library I have some material. I can see here is a CFRP. I want to add it. I will give this material to you. You can use in your project, or this is here in Excel sheet, and you can check some other resource or experiment, and you can find out these parameters, or consider to look in the manufacturing company's catalog. So they have the CFRP parameters and also the thickness, everything. So we go to here and check the what is here. So we mostly use ashen. You can come here, and here is called fiber reinforcement. So ashen is much more proper for this kind of composite material. In the ashen damage, here is we have elastic first. In the elastic, we have two choices to select: one engineering constant and luminance and density. Here is to another parameter, damage stabilization. You can consider some damage stabilization. So here is 0. You can give based on your experimental data. And here is damage evaluation. So we're considering the longitudinal tensile fracture energy, and also the compressive fracture energy, transfer shear fracture energy, and also the transfer compressive shear energy. And also we considering the damage evaluation and also the action parameters. Okay, and in the section we should create a composite section or composite lay. So I already said it's 8 layout 8, going to use conventional shell, and here is so in the here I can select all, and in the region I can right click and call edit region, so that region should select. This tool is in one direction, which is y, in the x, so I select them in 1 and choose this axis tool to see that axis 2 is giving here. And now in the material, select all, define the material, so the material is CFRP, and the thickness is, I go to edit and just give that number, and the angle, the first angle is 45, 0, 45 minus 45, and 19, 19, 19, and again 45, again 45, and minus 45, and 0. And here is the integration point in case if your project is very microscale, you can consider the integration point effect, so that for this one I can change this to 5. Okay, now again the second part, just I can go to here and copy this. Here I can call 2. Now what I want to do is just in the region, going to edit region and select this one and this one. Now here is, I created 2 regions. So now here the first one, and here is the second one. One more thing I should say, when we go to the assembly, let me bring the assembly here. We want to the thickness of the CFRP should be outside. So for this purpose, first I want to bring the CFRP, okay, and I want to rotate. Before the rotate, I want to rotate first, and this is the rotation, and then I want to take move and taking this point to this point. Now I want to turn on the assembly called rendering shell, apply. So I want to see some, let me go to section instead of section part, and we can see one is the red one in the part, the green one is concrete, and the white one is CFRP. So let's see here, and the problem is that the CFRP is taking center to center, so we want that should be outside of the concrete. So for this purpose, we go to the here in the first one, here is called offset. So we want to select bottom. Let's see how it works. So both are using called offset bottom surface. Now we go back to the assembly and let's see it's changed from inside to outside. In the both area it's showing outside. So now properly we uh, construct the both element together. So next what we're gonna do is we can assembly is finished, step is already given, we created two step and we created the two-step uh, output. You can check in the previous, I have given complete uh, explanation, and here is the interaction. So we want to create a contact between CFRP and concrete. So therefore we need to choose the two surface. We have two choice. One is we can consider uh, totally restrained, which is not allowed any deformation between or bond slip, and the second is we can consider some slip or cohesive behavior, uh, or even we can just consider the contact with a little deformation. But in this tutorial, just I will consider the using the tie, which is 100% constraint, and there is no any uh, movement between concrete and CFRP. So I can select here, create a tie, uh, concrete to CFRP. I can surface uh, go to here first. In the part I want to just see replace. Now I can select the surface which I want to create a tie contact, so the entire surface should contact together except this is 2n. And now here press the shift to select all surfaces. So now we selected all surface, and I can go to again is okay, and go to again surface. So then the second surface should be the CFRP. I go to the here and go to CFRP and going to replace. In the CFRP I can select CFRP and the CFRP will select it. So this one it's shell that you will select all. Now the inside is purple, outside is brown. So I select purple. So now inside is selected. Now we can go to back to see all structure is together. Now here is one more thing, in case maybe we should change the connection between the supports and concrete, and also the connection between these discrete elements with the CFRP. It's okay in case if we couldn't reach and receive any error, so it's okay, otherwise we should change it. First I ignore this and just I want to consider the contact between these two. It should be the concrete. Now here the interaction is finished. We go to the load is already created. Two load, one is two boundary condition, one is displacement, and we considering this is the roller connection support. Here is the mesh, so I should mesh this element and using 4, and now it's yes, and uh, everything is done, and I'm going to job, and this is called CFRP model. So the first one is concrete and the second one is CFRP. I want to submit. Now it start to running, and just wait for a while to see if there is an error we will fix. In other case, if it's start to uh, solve, and then so there is no problem. And now the first step is start 0.1 second, and there is not any error. We will let the program to finish analysis, and after it is finished, and we will check the result and make comparison together. So I will pause the video for a while. Now the analysis partially completed. It took about 0.2 seconds, but the time increment is quite small, so if I let the program to finish to solve this, it take quite a long time, maybe 10 hours or 12 hours. So I want to stop at this, kill it to see, because after this point the concrete is actually damaged, but the CFRP it has a quite tensile strength, which is not going to damage or yield. So we can go to check the results. Here is the result, and we can see the histories. Let me see just the CFRP replace. This is the CFRP. Even we can go to command this is about almost 280 megapascal it reach, but it should it will go to maybe 1000 megapascal. And we can go to here and the beam, and this is the beam, how the beam is behave. So it's reached to 80 megapascal with the ultimate compressive strength is 25 megapascal. We can do an animation and see how it behaves. We can check the tension strain damage. So it's already reached, and so significant damages happen to the bottom of the concrete. And if I go to the last step, so this is it. So mostly it's completed. So if I go back to here, create two. Here I want to create one more, and then I want to use this one, and this one I want to open the visualize. Go to the first one, I go to this one, result, and this one is the concrete with reinforcement rebar, and this is CFRP. So now we can go to here and just show the concrete uh, replace, and this is the concrete using damage. Now this one is rich because the tensile strength is quite high, and which has a contact with the CFRP, so it reached much more larger here. Even the time period is 1, which is 30 millimeter centimeters, 3 centimeter is pushed, but in here very small, because the stiffness of this beam is quite higher. Now we can connect them and showing a we created a connection. Now we can see the animation on one side, but we're not sure. Yeah, now we can see both sides and how it works. So in the first steps we begin start, and this one is larger, and finally in the middle is this one is quite high, but this one is less. So this is some difference, and other comparison is on the curve. So we want to create that curve in both sides. This is the EP which is taking from the 3 point, and we want to create one from the safe RP. Okay, and here is the curve from both sides actually. Now I can select this one. This is the 3 point or 3 without safe RP. Now I'm going to plot this one here, and this side here I want to create let's see, combine, and going to -1 times U2. Both are from same, but I should remove one of these, otherwise we will do some mistake. We cannot determine the exact. So now here I'm going to job and result, this one result, and going to gain and creating this 3 time history output. So this is the curve. I'm going to make an operation, putting combine and -1 times U2, and again comma -1 times REF2. So now save is called CFRP FET. Now we can plot this together. So here is the response of both beam. One is the reinforcement concrete, and the second one is which we provide CFRP. Now we can see exactly it's changed by 100%. So it's about 7, and it's almost 20 megapascal, 20 almost 200 kilonewton. So this is the resistance force. Okay, this is the comparison, and also we graphically shown. Now if you have any question, please put in the comment, and I will find time to answer you. See you next time, and you can find this tutorial files in the description link, and you can leave the analysis completed, and finally you can make comparison. See you next time. Hello everyone, this is another Abaqus tutorial. In this tutorial I'm going to show you how to model this circular column or reinforcement concrete circular columns in Abaqus. So this is just one of my friend or followers asked me to model. So this is very simple, and we will then perform our compressive test, and also we will, in the next tutorial, we can consider eccentricity effects or impacts to the column behavior. But in this work, just we will apply a concentrically load on the top of the column. So the column has 2 meter height. This approximates a short column and about 500 millimeter diameter. The concrete cover is 30 millimeter. The rebar or longitudinal rebar is 20 millimeter diameter, and spiral or shear rebar is about 6 millimeter. So we're going to open Abaqus and first column. I can call column circle or circular column. Or circle or circle. So now we're gonna I will use millimeter, so I can use 2000 millimeter, and drawing a circle 0 0, and then I can give the radius. The radius is I can live anywhere I want, so but then I'm giving here the diameter is 250, and now I want to give the length or height 2000 millimeter or 2 meter. So this is the concrete column, and next I want to call stirrups, or sorry, this will be spiral. Spiral, we should call spiral, and we're using wire and planar. And now I can give again using circle 0 0, or I can 0 0 and giving, but in the previous one was 250, so we want in both sides, so 30 millimeter, so then it become 220. So the third part is just this is okay, done, and spiral is done, and this time I'm going to add called rebar, longitudinal rebar. So this is also using wire, and I can use 0 0, and so I want to give about let's suppose 1 centimeter cover in the bottom and the top. So that's become 1980. So this is it, and we finished this ray. The material we want to use is so I have some available material, I want to add it. So the material is using concrete CTP 25, and the steel material is let me use this material. I want to use this material. The material concrete CTP is a CTP. So this is the elastic, and this is the density, and this is the elastic modulus, and this is the damage parameters, and this is the compressive parameters. So maximum 25 megapascal potential, and also you can open the sub option and the damage and cracking strength. So this is the steel material. So mostly this steel is ST737, and this is the elastic modulus, and here is the plastic behavior, which ultimate 470 megapascal. I will give the link of this model. You can in case if you have some trouble with the modeling, you can use it. And now I'm going to create concrete. The concrete is solid imaginist, and I'm going to use concrete, and the second is going to use rebar. So rebar, and here I come to beam, and I use truss. This is called rebar 20 mm. So rebar 20 mm, the first I should use the material, and the second the cross section. So I can use calculator and to calculate. So the area is calculating pi 3.14 times 400. So 20 by 20 become 400, and equal divided by 4. So this is the area of steel this rebar, the steel D20, and the rebar 60 is 3.18 times 35 divided by 4, 28.2. We call this spiral, and this time using the same material, but 20.26. Now I'm going to assign this material here. This is the rebar and rebar 20, and this is spiral and spiral, and the last one is circular color. So the material is added. Now we go to the assembly. First, let me bring the column and apply, and spiral, apply, and the last one is rebar. Okay, now all we're gonna do is, let me do some before doing something. I'm going to turn on this one. You can see the exact location of these things, and I want to first rotate these, rotate using I'm going to use this Z. If I Z means that it will go to like that, but we're gonna using X. I want to use X, so this is X. No, going to using the Y, so like this. Now I'm going to shift this or move it to this point. So now exactly this both element is in the same place, but I want to move using this command, and I can select this one, and I can go to use this command, remove, and I want to take this one, let me take the point 0 0 and pushing moving to Z by 0 positive 20. That's it. So next I want to select this one. This one should be select 0 and push 0 0 10. So now it's quite right place, and I'm going to using this command, and this command is we call the radial pattern, and before we use this linear pattern. So I'm going to using this one, and it asks me how many you want. So I want to, this pattern should be 8. So this is 8, so that 360 divided by 8 divided let me divide 360 divided by 8, so this is 45, so the angle should be 45. Now it asks me select the axis, so I'm going to select the Z, and you can, this should be 45. Is it okay or not? Uh, 360 is okay. We should give the 360, it means 8 number to the 360. So now we finished here, just okay, and we can go back here, and this time we use a linear pattern and adding this one to this direction. You can select here, and this one should be 0, and we're gonna using 100. this is 100, and I'm going to extend this. And this is it. Now we created the entire reborns and spirals, and I'm going to go here, display option, and I'm rendering the P. Now this is the circular column prepared. I can go do one thing. I can move this little upper by going to take this one and selecting this one and selecting 0 0 and just going to 0 0 and pushing to 20. Now it's okay. Now we can bring the concrete column again. I can see here is inside the column. Now I can select all and rotate using this select all and selecting this axis, and I'm gonna go to use minus 90 degree. So now here is okay, no need to add another movement, so just in the right place. We finished in the assembly. You can see here this one, and we can go to that step. So we have 2-3 options. You can use static, implicit, explicit, with whatever you want. But let's play with them, and I'm going to use explicit, called dynamic explicit, and I'm going to select explicit, and let the time is be about 10 seconds, and other parameters as a default. And here I want to activate some list the interval should be 250, and here I want to use some failure output to see the structure and the column damage, and here is also the state using this state, and this is okay. And we can create some reference point. Let me call reference point, and I'm going to create a seed. That reference point called displacement. So actually we don't know the capacity of the column. By applying a displacement in the top of the column, so we will get the capacity of the column. So the next time then we can use that capacity load to see the deformation. But now also we can apply the displacement and see that we can also observe the capacity and also see that the deformation and also damage. So I'm selecting that point, okay, and we created one set. Now here in the output, in the time history output, I want to create one output, that's the displacement in that point and also the reaction force. And I can go to use set using this one. So interval is making 200, so you will get better, a smooth curve. And now I'm going to select, which is REF2 y direction and also RE2. And now we can go to the interaction. So the first interaction is, let me couple this point to this area, and I'm going to use coupling and selecting this point, and next I'm going to use this surface, and it is a coupling. The load applying is in the center of this column. We can consider create this node a little out of that center, so then we can consider ecocentricity effect in this column. So that's the next tutorial we will discuss. And now we want to use an embedded region, which is the reinforcement is embedded in the concrete. Now I can go to here, just going to here this one, and from sorry, go to back part, and I'm going to circular column to remove for a while, and I'm going to select all these rebar, and I can go to select region, and I can go to back here and select the concrete. Now the concrete is selected. So we created embedded region for the two material. Now we finished. We go to the loading, and we want to create a base fixed base in the bottom of the column, and here is, and we want to create a displacement in the second part, and I can go to here, select the previous defined state here, and just want to, this other should be fixed, and other in this one should be minus 10. Now it asks me to define a amplitude, so we're gonna 0 0 and 1 should be 1, so it means actually we have 10 seconds, so in the 10 should be 1. We're gonna apply this one, and now we apply the load. Now we can go to the meshing, and we want to create a mesh. Here is the mesh. We can change this mesh by creating some partition. If I go to use this 3 point, and I can select this point, and this point, and also I can select all, and again I can select this point, and this point. Now we create it, and also I can do one more, but it's enough. I'm given a number that 200 is very high, and I'm going to 100. So the mesh is I think it's coarse mesh. It's better to make a, but for the fast performance we should make logical meshes. And I can define the material. Here is the explicit. I can add explicit, and this is done, and we go to the job. Go to the mesh. Let me change this mesh, and the mesh is can be 75, or it can be 50. I forgot to mesh the other elements. Let me mesh the rebar, and here is 200 is okay, and yes, and also I should change the to trace element, otherwise you will get error. So this is also trace here, and is 100. It's okay. Now we can see the mesh is okay. I think it's, let me make it that 75 is, or 100 is 100 is okay. Now I can go to job and submit the job. Column test. We're gonna submit it. It's called in the following model, constraint are applied at region that have been either related named as constraint. Boundary condition 2. We're gonna go back to the load. Boundary condition 2 is actually, I should go back to here, reference point. I should create reference point, because after the reference point is now exists, then I'm going to back to here to set define, and that point now it's fixed. Submit it in a model. The following constraint apply to region. So the constraint 1, because we meshed, so there is the constraint 1 is missing the point. So control point is this one, and surfaces exist, and now it's okay. Submit. Or we can check the monitor, and it's starting running the analysis. Okay, let's ignore this one. Now it's the first step, and this is the first step, which is 0.2 second. So it will take about maybe 1 hour or less than 1 hour to finish. So I will pause the video. After finish, we will discuss. Now the analysis completed, we can go to result and see some performance. Let's see, this is the one mesh stress. It's reached about 30-40 megapascal, and I can go to here to see the damage. So the damage is compressive damage, so mostly it's in the top of the column because the load is close to this area. And we can also see this is the same, it's a sort of diagonal. Now we can go to see the scalar degradation as well as go to the displacement. So the displacement is mostly in the top. Now I can go to the output, create the output, and previously we defined these two, and I'm going to save it. So here is the giving curve, and I want to combine this using combine function and giving a -1 because it's in a negative times 2ut u2 and comma and -1 again times 2 REF2. Now we can save it as force displacement curve, and I can go to plot that one. Now here is the column capacity, and this is about 500 megapascal 500 kilonewton, and the displacement until 5 is the maximum displacement, or the column maximum displacement. But after that, so the column will deform or fail. Now we can go to here and see that the data. So this is using Newton, so when we convert into kilonewton, it's about 500. So it is 500 or 5000. Let me go to we can export this data to Excel sheet. I can paste it here, paste, and I want to use general number, and I want to take this here, and I want to use this one divided by 1000 to change to kilonewton. Now I can plot these two curves. Yeah, it's 5000. So this is 5000 kilonewton, the capacity of this column, with a maximum displacement of 5 millimeter, approximately 5 millimeter. So this is the capacity curve, and you can next time you can go to take this load and apply some sort of failure. Okay, this is the end of the tutorial. If you have any question, please put in the comment, and I will find time to answer you. See you next time. Hello everyone, this is another Abaqus tutorial. In this tutorial, I'm going to simulate a steel beam column joints to evaluate the behavior of the welded beam column joints. The material we use in this simulation is steel Q235, which has a yield strength of 235 megapascal. So we will see some failure behavior, which usually I call shear failure, and the shear failure is 0.5% of the yield strain, and the column size is 200 by 200 and 50 millimeter thickness. So it's called a box section. The beam is also a box section, but with different diameter, so 150, 120 and 20 millimeter thickness. Then we will apply a boundary condition in this region, and in the end of the beam I will apply a load. So the load will be as a push, just we will push by 20 centimeter, which is equal or almost the size of the width of the or height of the column. And you also can do it using other connection, such as weld connection or end plate connection. But just for simplicity, how you can properly model this behavior, consider just the connection. We go to the Abaqus. Here I have already modeled, but I want to show you from the sketch, and I'm going to select here, rename it. Okay, just going to model 2. Create a model. I can here I can take a new one, and that's already saved, and I want to create the first column. And column, we can use solid elements and also beam element, but for better understanding, just I want to use shell element, using shell element extrusion. And the first I want to give the size of the rectangle, which is 200, so it's b minus 100. Or even I can, without giving the number, I can draw a rectangle and give the dimension. So this is 200 and 200, and the length is 1000 millimeter or 1 meter. So the second part is beam, the same method, and the size is 120, and the height is or depth is 150. The same dimension or length. We finished, and we go to the define material. The material, I have here the material in my library. I'm going to add it, and you can see what is the properties. Even you can check in the or Google it, you will get this properties material. The density is because I want to consider some failure criteria, especially I will consider the shear failure. So the shear failure just supported by explicit analysis, so that required to conduct a dynamic analysis. For the dynamic analysis, we should provide the density for the material, 7.85 E minus 9, which is Newton per cube meter, and the elastic modulus is about 119, and you can also take it to 100,000 megapascal or 200 gigapascal. So the Poisson ratio is 0.3. The plastic is I also considering some degradation. Here you can also consider that's also allowed in Abaqus, and Abaqus can support this. This is almost the behavior of the steel. So the steel curve first start in the elastic region and then go to the plastic, and then again a little degradation, and then it quickly drop down. So we can consider that degradation as well. In some tutorial, just we consider until this area, but it's approximately true to can consider this as well. So I will take this one. In case if you have any doubt about the result, you can delete and you can check this area and again add these parts and compare the result how this behave. Now it's okay, and we want to define two sections. One is for column, which has using shell element homogeneous, and it's 20 millimeter for the beam. Beam is 15. Yeah, so that should be 15. I'm going back to here, and that should be 15. and the second one is for beam. This should be 20 millimeter in the same material. Now we created this two section. I'm going to assign it. This is beam, and I'm going to add beam. The second is column, and I want to add column. Now it's okay. We created both material, and before go to the assembly, I want to create some partition for the column because during the meshing and the contact, there will be some later the distortion in the joint in that joint. So I want to prevent that distortion and also some disconvergence. So it's better to create some partition and create that specific line which is passing in the other elements. So I'm going to select this one here called partition face. I'm going to select this face and just enter and take this line. So now I know the size of the one I want to give this line to this line here, and one again this line to this line, and the depth is 200, but the depth of column is 120. So I'm asking to these two should be 20, and these two also should be 40. And so now I can measure these 2 points is 120. So what's next? I'm going to give one here and one here. Now I can take this one. The total length is about 1 meter. Take this dimension, and the total length is 1 meter. So we have the height of the beam is 150. So when we divide it by 2, then it become 250. So this should be 250. So and I'm going to use the same for here, 215. So the total become 850 and 115 is left. If I go to this one, 150. And now we created, this is 150 and this is 120. This is 120. Now I can, so some area is over dimensioned. I'm going to delete these things and it will be okay. Now we can see we created a very nice partition. Now I can go to the assembly, and I'm going to bring a beam column, and I'm going to use this offset to be out of each other. Now the next, I want to rotate using this dimension, this location, and one more using this. That should be 100 minus 19. That's other side, and I'm going to select it again, and this time I'm going to give 180. So it will be selecting this one and asking 118. So this is the correct, and I want to bring rotate the beam as well. So this is the beam. So one, you should take this one, and again going to be here. Okay, and this time select this one and selecting this one more, and instead of giving 118, I'm going to back here to give minus 90. And now I can use the translate option, and I'm going to putting this point to this point, so exactly in the right location. Now I can go to here and see it's correctly adjusted. I'm going to move all and selecting that point to 0 0. Now here is we finished in the assembly. We can go to the step. I want to conduct a dynamic analysis, so I want to call it a dynamic. In the dynamic, I want to use explicit, and here is the explicit dynamic. The method which I want to use is looks like static, which the time period is about 1 second. In case if I use a very short period of time, that means that's quite fast and seems dynamic. But in 1 second, it means I apply the load slowly. Even I can increase to 5 seconds. As much as I increase the time period, so it is changing the behaviors from the static and from dynamic to static. So other parameter is as it is or default, and next I want to create some a reference point. I want to create a reference point here, and this is first creating some data point and to find out the center of that column. And now I want to define the reference point. So this is the reference point 1, which I want to apply load in this point or the end of the beam. And this is the in this region I want to define some stiffener, which I will restrain this area. It means we are not discussing above of this area, so we want to totally restrain this area and we not allow any deformation in this area. Just we will consider the deformation across this joint, and specifically this area which we considered as a weld. I'm going to back in assembly. We're not using some contact. Even we can use tie or even contact, surface to surface or node to node, but there will be some instability in this area which will not solve our problem. But instead we use merge, that means that giving us a very manufactured style for the beam column connection. Looks like 100% fixed and rigid. So when I call it beam column joint, giving retain it and geometry, and I'm going to select this one and these two. Now we made that both column beam in a single element. Now again, because during the merge, so the other data will remove, so I should redefine the 3 points and 3 reference points. Okay, now here is reference point and the first reference point and the second, and now we created them, and I want to define a seed. The seed is called loading point or loading. So this is the loading, and we go to back to here. We defined the steps, and we consider that default output, so that contact is no need, we can take it, and the interval can be, let's make it 200, and here is the output. I want to create an output using that set loading, and here I want to get as in 200 from 200 interval, give that displacement in the vertical dimension and the actual force in here. Instead of applying some concentric load, we'll apply displacement. So we push until the total disconnection fail. So then we will measure the displacement. So when we apply the displacement in this point will create reaction force. So just you taking your finger, you're pushing some specific location, and there will be vertical reaction force on your finger. So that means when we are applying the displacements, you will get reaction force. When you're applying load, then you have to get the reaction force from the boundary condition. Okay, we will select the displacement in U2 and also REF2, and okay, now we created the displacement as well. And the last one is going to the load, sorry, interaction. In interaction, what I said, we want to restrain other three parts because we are not considering the top of the column or bottom of the column, just we want to focus on this region. So that means we want to restrain and create some sort of stiffener in these two. So by you can use tie, you can use rigid multi-constraint point, or you can use coupling. Any of them is okay. So I will use I want to use multi-constraint point, and you can use tie. So let's see what will be the difference. I'm going to select that point, and that point is a master point, and other edge is the slab point. So I'm going to select it, okay, here like this. That multi-constraint point means we creating a rigid diaphragms in that area, so the deformation is not allowed. Now we can go to the second and selecting this point and this area. So after the result is out, you can see there is no deformation in this area because our focus is in this beam column joint. Now the third one is also multi-constraint point, and here it is. Now we created. The next thing is we want to go to the load. In the load, we want to apply a fixed boundary condition in this area. In caster. So because we will not allow any buckling of this column, and the column is quite strong. Next, we want to apply a loading as a displacement here. Selecting this point, or you can go to the state, taking that point. So now it's in D. I'm going to use a minus 200. So it requires some amplitude. You can go to in the 0 0. In the 1 should be 1. So it means in a time period of 0 is 0. When it reaches to 1 second, so it will take this 1 amplitude times to this 200 millimeter. Now here I can select. Here is the load is applied. Now we don't have anything else, and just we should apply the mesh. Here in the meshing, we want to create a fine mesh. Even you can select these elements, using a fine mesh. In other element should be coarse mesh. It doesn't matter because the most important area is this area. So this part here. Now we can say mesh yes. So the mesh is totally uniform fine mesh. And now here is the element type, and we should define the explicit method from here. And there is one more thing in the integration factor. When we have especially beam element and also shell elements, there is some integration point across each element. So now this is one element. In each element there is 5 integration point. So that 5 integration point means we integrating in each question 5 times. So that needs a lot of time. So we can check reduce the integration time. When the 2 integration point is same and program will determine, you can reduce. And one more thing, because we will define some shear failure, we want to use element deletion. So we want to activate these as well. Okay, now we finished and we want to go to job. But before job, we didn't define a timeout the shear deformation. So what I'm going to do is I'm going to edit the keyword, and instead of adding in the material part there, so I'm going to add that one here in the after the plastic, and I'm put one star and call it shear failure. So you should write correctly and give 0.05%. Even you can give 0.4%, which means the plastic reached to 4%, it should start to fail. And then you can give a comma and it will start to use these properties in the analysis. Now I can go to call BCG model or beam column join. I'm going to submit it, and you can use some parallelization and you can use multiple processors, but mine is okay. Submit. The job is submitted, and here is the running start. So we used a very fine mesh. 25mm is fine mesh actually, so it will take some time, just a while to see the result. Now it start to running, and it take some time to finish, maybe about hours or maybe half hour. So it's about 0.35 second, so we should wait for a while. Now the analysis partially completed. It took about 0.4 second, and I'm going to see the result and if there is any element deletion, and that seems it didn't reach to 0.4% yield strength, but it already reached. Some element is deleted here. These 2 elements is deleted. If I shown a animation, you can see exactly that top is no deformation because we define a multi-constraint point and this area, and the most stress concentration is in this region. And here finally in the bottom is removed 2 elements, and the top also, yes. So we can go to the option and let's use this option, and we can see this element is deleted. And also we can use the rendering, and this is the rendering, and we're gonna see this element is deleted. Now we can draw the curve, the force displacement curve, we can go to output, and we have created already two time history output. I'm going to save it as it is. Yes, we got the deterioration, and I can go to, this is a little noisy because it's dynamic, so we want to use a sort of a filter. Let's using this filter, and I'm going to give the data x, y as a or f, and the frequency, let me give 1 and see how it looks like. So this is pretty well, and I'm going to save it as RF, and the next I'm going to use combine, and taking this U1, U2 and that RF here, but I should times -1 because it's in a negative direction. I'm going to -1 times this one, and here after the comma, -1 times RF. So I'm going to plot, and you can see it's in a positive direction, and I can save it, called FED, force displacement curve. Now I can delete others, delete it, and just plotting this FED. So I can go to see here, and this is the response curve, which we the structure go to about 50 kilonewton. So after 55 kilonewton, it's still not degraded to 80 millimeter. We can check it in edit if there is any degradation. In between this 3 point, it's same, it's no any load increase, and between this, so it seems after this point it will degrade. We can stay a while and see the other response. So I will put this model in the description link, and you can complete the analysis and check like this and see. So we got the displacement curve, and you can use some simple mathematical equation to get the deformation or the rotational angle using this curve, taking the rotational angle. So that's all for this tutorial. Let me check the last parts. Yeah, here is the element is deleted, this element, and this element is deleted, and this element is deleted because the stress concentration is in this region. Now and we can see more. So this is the end of the tutorial. If you have any question, please put in the comment and I will find time to answer you. See you next time. In next tutorial, I will conduct the reinforcement concrete under earthquake simulation.